This is lecture 9 in Principles of Metabolism. In this lecture, we'll look at energetics and enzyme catalysis. So the basis for all the energetics that we'll look at in this lecture is really that all reactions always strive to minimize energy. And specifically, they strive to minimize a quantity known as Gibbs energy. So this is a quantity that you can calculate for pretty much any molecule that you have in a particular state, if it's at a particular temperature and with a particular concentration and so on. It's not easy to do, but there are tools out there which lets you do this. So there are databases also where you can look up these values. And we won't go into the details of exactly how this is calculated. But we can get to these values. And so for any reaction that we are interested in, we can simply compare the energy of the reactants, of the substrates, and of the products. And you can pretty much take the difference between the products and the substrates. And so if this difference is negative, then it means that the reaction is causing the substrate to lose energy as they form products. And that means it's favorable. So this is quite similar to the concept we encountered before when we looked at redox oxidation reduction reactions. There we saw that in a redox reaction, when electrons tend to go to a more favorable state, we get a lower energy compound, and that's always favorable. So this is similar, but the Gibbs energy concept is more general and really captures all the energetics that's relevant in metabolism. So that's a general rule. Negative Gibbs energy difference, then you have a favorable reaction. And I'm sure most of you have heard about this before. So that's the way of describing it. You have substrates at a particular Gibbs energy level, and as long as they fall down towards a lower level, then you have a favorable reaction. So you might note that we have a delta G with a little degree symbol on it here. So those are the standard Gibbs energies that you can find in tables and in databases online. This depends, the Gibbs energy depends on the actual concentrations that you might have in your system in a cell, or maybe in vitro if you're studying an enzyme in vitro. So we may have to readjust this though. So the actual delta G that we're interested in depends on both the standard value, which we put in here, and then it depends as the logarithm of the reaction quotient, which is the products, concentrations of the products divided by the concentrations of the substrates. Which means that if you have a lot of products, you see this is a very weak dependence because it's logarithmic, but if you have a lot of products and very little substrates, then this term is going to start to get large. And when that happens, if it gets large enough, the delta G is going to turn positive. So that means that if you have a lot of products, it's going to push the reaction in the other direction towards the substrates. So that makes sense. That's what we recognize from basic chemistry. And from this, you can also figure out a relationship between the delta G and the equilibrium constant for reactions. So those are the basic rules of delta G and the Gibbs free energy difference. So we saw the Gibbs energy difference determines whether a reaction will happen or not. So if the delta G is negative, then the reaction is favorable, and it's going to occur sooner or later. But we don't know how fast the reaction is going to go from this. So the delta G doesn't tell us anything about that. So that instead depends on another quantity, the activation energy of the reaction. So this is a kind of energy barrier, and it has to do with the fact that in order for a reaction to occur, the substrate has to usually form some type of higher energy intermediate or some kind of activated complex before they can go on and sort of fall down and become products. So this energy, the amount of energy you have to put in to go over this barrier, that determines how fast the reaction will go in the direction from substrates to products. And this dependence is very strong. So the activation energy strongly determines the reaction rate. And it's an exponential type of relationship. So as this activation energy increases, the reaction rate drops exponentially, so very fast. And so you will see these type of relationships a lot if you dig around in energetics, in metabolism. You usually have an energy, and then it's usually scaled by a quantity, R times T. R is the gas law constant, and T is the temperature. And basically this quantity is the amount of energy that you have sort of in heat at room temperature. So it kind of scales the energy by how much thermal energy you have in solutions at room temperature. But so anyway, what it comes down to, if you calculate this out, is that the reaction rate decreases in half about every 3.7 kilojoules. So that tells you how strongly this depends on the activation energy. So for example, if you have an activation energy for a reaction of 50 kilojoules, then you can calculate quickly that this is about a 10,000-fold decrease in the reaction rate compared to having no energy barrier at all. So this is a very strong dependence, and fairly small energy barriers will really determine the reaction rate strongly. So I'd like to emphasize this difference between favorable reactions that have a negative delta G and spontaneous reactions. So in metabolism, most compounds, metabolites that we encounter, are stable, reasonably stable in water. So that means that they may interact in reactions and may be able to form products, but this doesn't happen just by itself. So ATP is an example. The hydrolysis of ATP in water is highly favorable. It has a large delta G associated with it, liberates a lot of energy, but it's not spontaneous. It doesn't happen by itself. It has a fairly large energy barrier that prevents this from happening. And this, of course, stands to reason that all metabolites that we encounter should be like this. Otherwise, they would spontaneously break down or react with things in the water environment of cells, and then they would be useless. And such metabolites will probably have been sort of weeded out by evolution a long time ago. So this is generally the picture we expect to see, that the metabolites we deal with when studying metabolism, they might take part in reactions, such as this one, but that doesn't happen spontaneously. So high energy compounds like ATP are not unstable in any way because they are high energy. The stability and spontaneity of reactions that has to do with the energy barrier. So the energy barriers that are in place sort of ensures that these metabolites are stable. So that's good to keep in mind. So as I'm sure you're aware, the way cells make metabolic reactions happen is by enzymes. And enzymes make reactions happen by lowering the energy barrier. And that occurs because without an enzyme, as we said, there might be a very difficult transition state which has high energy that the reaction sort of has to cross to get to products. But with enzymes, there's usually some more convenient way for the reactants, the substrates, to bind and sort of join each other. So it's easier for the reaction to happen, and therefore this energy barrier is lower. The activation energy is lower with enzymes. And as we said, there was an exponential relationship between reaction rate and the height of this barrier. And there's this value about 3.7 kilojoules, that the rate doubles every 3.7 kilojoules that you lower this energy barrier. So enzymes can, because of this exponential relationship, enzymes can affect the reaction rate very strongly. So it's not uncommon that reaction rates can be improved 100,000-fold or something like that with enzyme catalysis. So essentially, enzymes are a way for cells to turn on and turn off reactions. And it's important in this context that, as we said before, that the reactions without the enzymes actually have high energy barriers, because that means they will not be spontaneous, and the cell has the option of turning on an enzyme, because these things can of course be regulated to choose to do this reaction. So this now gives an opportunity to carry out reactions at will, on demand, depending on what is required by the cell. So the energy barriers are important in this sense. The other important function of enzymes is that they can couple reactions together. So this happens because enzymes can bring substrates together in a local environment where they can interact. And in this way, they are able to let favorable reactions drive unfavorable ones. And this is really important, because this is really what lets enzymes extract energy from metabolites when they are oxidized, for example, and use that energy to drive other reactions that would not be favorable otherwise. So here's an example. This is one of the steps in lower glycolysis, converting phosphoenol pyruvate to pyruvate. And this is a highly favorable reaction. It has a large delta G of 70-something kilojoules per mole. So this is strongly favorable. And if this reaction happens on its own, it's exothermic. It releases a lot of heat. And so this large energy difference is used by cells, exploited by cells to create ATP. So the enzyme that couples this to ATP synthesis is pyruvate kinase. And ATP synthesis itself is unfavorable because, as we know, the usage of ATP, the hydrolysis, is favorable. So this is the reverse. And what you can do now is, in order to figure out what the net reaction, how that will look, what kind of delta G it will have, you can simply add the reactions together. And so this is a property of the Gibbs energy. You can just add stuff together, which makes it very convenient. So if we add these two reactions together, some of the things will cancel out. You will get rid of the phosphates and the water, and you can add up the differences in Gibbs energies, and you come up with this final reaction. So now we have a coupled reaction where you are using PEP, phosphoenol pyruvate, to drive the phosphorylation of ADP to ATP. And as we saw, the phosphate group dropped out here, so it's actually this phosphate group that is put onto ADP to make the triphosphate ATP. And in the end, we come up with a reaction that still is favorable, has a delta G of 27 kilojoules per mole in this case. So this will occur in the forward direction, and the enzyme can, of course, ensure that the energy barrier is low enough so that this will occur with a reasonable rate. And in the end, we have now extracted some of the energy inherent in this conversion of PEP to pyruvate to make ATP. So that's really a key step of enzymes, and this is what enables metabolic networks to function. So I'd like to point out one property of the Gibbs energy that's not talked about so much in biochemistry books. So if you read Stryer or any other biochemistry book, really, you'll probably find a statement saying that the delta G of a reaction, the Gibbs free energy difference, provides no information whatsoever about how fast the reaction goes. So that's true about the forward rate of a reaction. So if you have something that is irreversible, that's absolutely true. Then it's only the activation energy that determines how quick a reaction will go. But most of the reactions that we encounter in metabolism are reversible. And this complicates things a bit, because it's kind of like you have two reactions that happen at the same time. And so things are a little bit more complicated. So just to recap, what we said about reversible reactions is that we can think of it as we have a forward rate, sort of a reaction going in this direction, and then we have a reverse rate, so the product can go back and form the substrates. And what we're usually interested in metabolism is the net rate, which is the difference of the forward minus reverse. So in the end, where is the net flux through the reaction going to go? Is it going to go forward or backward, and how fast? And then there's this exchange rate, that is the amount of flux that is just going back and forth between substrates and products. So that's a reversible reaction, and you can think of it as two reactions sort of on top of each other, the forward and the reverse. So what does this mean now for the energetics? Well, so if we draw this diagram again, we see that if we think about the forward reaction, it's what we said before. We have an activation energy, and this completely determines the reaction rates, and then the substrates sort of fall down and become products. But if we think about the reverse reaction, well, we have a new type of activation energy. It's this number, but it's also this distance, which is the negative of delta G in this case, because delta G itself is less than 0. So we get this number, EA minus delta G. So basically there are two activation energies. There's one in this direction, in the forward direction, which is this large. And then we have an even larger activation energy for the reverse reaction to happen, for something to come back again. So what happens now? Well, the forward rate depends only on this, but the reverse rate depends on this. And here we have the delta G again. So you can easily see from this figure, if you have a highly favorable reaction with a large delta G, the reverse rate is going to be very slow. And that means that the net rate, which of course is the difference between the two, will actually be affected by the delta G. So more favorable reactions in general will have a larger net rate at the same activation energy over here. So this statement that delta G has nothing to do with the rate of reaction, keep in mind that has to do only with the forward reaction. The net rate, which we're usually interested in, this is not true. So what happens with enzyme catalysis? Well, as we said, enzymes lower the energy barrier. And of course, what will happen is they will lower the energy barrier sort of in both directions for both the forward and reverse reaction. So what happens with enzyme catalysis is that the forward and the reverse rates increase. So actually it is this exchange rate that is increasing. And you can see if you have an enzyme that lowers this down to almost 0, then you have a situation where the forward reaction happens very fast, and the net is really completely determined by the delta G, because it's determined by how much of this is going back again. And so you can see if you have a large delta G, you're going to have a very fast reaction when it's enzyme catalyzed. And if you have a small delta G, it's going to be basically most exchange flux going back and forth. So the delta G is important. It's a bit more complicated than you will see in most textbooks. One way to express it is like this. If you sort of do the math, you calculate the rate forward and the rate going backward, and then you take the difference, you can come up with this type of an expression. That if you look at the net rate as a fraction of the forward, so that means of all this flux, how much is in the end going from substrates to products, then you get in a relationship that looks like this. Again, you have one of these exponential type of relationships, so it's delta G scaled by RT. And what does this mean? Well, this means that if the net rate is almost as large as the forward rate, so that if most of the reaction is going forward and there's very little reverse, then you're up here. And that happens when you have a very large energy difference. So something that falls down rapidly, then you will have pretty much everything going forward, nothing going in the reverse. That makes sense. And in the other extreme point, if you have a delta G which is very close to 0, then you will have a net rate which is the same, which is 0. And so all the forward rate is actually just exchange flux. It goes back again with the reverse rate. So here you have equilibrium. Both of the rates are, forward and reverse rates are equal. The exchange rate is everything that really matters. And enzyme catalysis in this case will just make the exchange rate go faster, and it will not affect the net rate at all. Okay, so a lot of rates. This is a little complicated. But take a look at this, and it's this can be important to keep in mind because it actually affects how we analyze energetics and metabolism. So now, because the delta G of a reaction actually affects how fast the net rate will be, there is a trade-off here in oxidative metabolism between how fast you can catabolize something and how much of the energy difference you can capture as ATP. So this has been debated a lot for glycolysis in particular, because it turns out that if you look at lower glycolysis, going from glyceraldehyde, or really glyceraldehyde phosphate, but to simplify a bit, glyceraldehyde to lactate, you have a delta G of about 100 kilojoules in lower glycolysis. And there's several steps here, but in total, this is what you end up with. And so you could potentially take out 2 ATP from this. You could have a yield total of 2 ATP in lower glycolysis. But that's not what we see in nature. You see that there's only been 1 ATP coupled to lower glycolysis in the end. So there's a large delta G that is remaining. And why is that? Well, so we should remember this delta G is actually spread out over several reactions. So each reaction is not this favorable. But there is in the end a fairly large amount of delta G left. So why is that? Well, so it has to do with this phenomenon that delta G actually affects rate. So you can imagine a cell could choose, if it has the enzymes available, to couple 2 ATP generated to lower glycolysis. But then the delta G would be very small, and so the net flux would be small. So you would get a high yield. You would get 2 ATP rather than 1 for each glyceraldehyde you break down, but it would go slowly. And so, of course, in the end, the amount of ATP the cell is able to extract per unit time would be important if it's competing with other cells. So both the yield and the rate is important. They sort of multiply together. And it turns out that cells have chosen to take 1 ATP and let the rest of the free energy difference, the delta G, sort of be available to drive the reaction quickly. So this has been analyzed in some detail. This is a fairly advanced paper in Nature Chemical Biology that looks at this and looks at the details of glycolysis in some depth. People have studied this when it comes to aerobic glycolysis, which is this phenomenon where glucose is broken down by glycolysis and not used for respiration, even though oxygen is available. So this happens in yeast, for example, and it happens in cancer cells and many proliferating cells. So there is this phenomenon in yeast, for example, the dioxic shift, where as long as large amounts of glucose is available, it's just glycolized. And you get ethanol in this case in yeast. And when it drops, then you start oxidizing, and then the cells grow a bit slower. And so the cell really chooses to use glycolysis and exploit this large energy difference while this is possible. And only when glucose becomes limiting does the respiration set in. And respiration is thought to have a smaller delta G, so it's thought to have a lower rate in that sense, but a higher ATP yield. So this is a balance that microorganisms try to strike between these two properties. There's also been some studies on communities trying to figure out what kind of choices do microbes make when it comes to glycolysis. And some argue that there is a sort of tactical advantage to doing glycolysis rather than respiration, even in the presence of oxygen, because of these trade-offs. So this is a bit controversial, and there's certainly lots of other theories and sort of potential explanations for aerobic glycolysis. But it's clear that there is a trade-off between reaction rate and yield of ATP. Or in any other situation, there is a trade-off between reaction rate and yield of anything, really, that you use energy for. So this is a fact that's important to know about. Now, lastly, I would just like to quickly cover something about Michaelis-Menten kinetics. This doesn't really have to do with energetics in the terms of free energy and delta G, but it's an important property of enzymes. So I'm sure everybody are familiar with Michaelis-Menten in some form, and so there are these fairly complex derivations of why you get this type of kinetics for enzymes. I don't think that's so important for us, but the Michaelis-Menten type of kinetics, this type of situation where the reaction rate that an enzyme has varies with substrate concentration, and it decreases quickly in the lower range, and then it kind of saturates and moves towards a maximal rate. This type of description of how the enzyme function is a good sort of, you can think of it as a phenomenological description. So it's just, this is how it behaves, and we don't really have to care about exactly why. It's just a good picture of how enzymes tend to behave. And why is this useful? Well, the maximum rate of enzymes is mostly useful, I think, for studying enzyme sort of function and detailed mechanisms. And we're not going to think about that so much. But the Michaelis-Menten constant, Km, which is the substrate concentration where the enzyme rate is half maximal, that says something about how quickly the enzyme saturates. This parameter is quite useful because it tells you something about how saturable the enzyme is. So at what concentration of substrates is the enzyme going to start working efficiently? So this is kind of the responsive range towards around Km, plus minus some factor, but somewhere around Km. This is the responsive range of the enzyme, and here is really where you would expect substrate concentrations to be in a cell so that the enzyme can respond to them. It doesn't make much sense for a cell to have enzymes which are completely saturated all the time. So you would expect that this is kind of the physiological range. And these Km values can be determined. It's done in vitro. And it's a little difficult. You can find databases like Brenda where you can find these Km values for enzymes. But they can vary quite a lot depending on exactly what the chemical conditions were when people did the experiments and determined these values. So it's not uncommon that you can see a tenfold sort of difference between some published papers on the same enzyme. It's a little tricky. But still, there's data about this, and it can be useful. So what is it useful for? Well, classical example of how to use this is to study the type of environment where a particular enzyme is active. And so the classical case is glucokinase and hexokinase, I would say. And so here you have a situation where glucokinase, which is an isoform of the enzyme that phosphorylates glucose, which is expressed in the liver and pancreas. So this isoform of the enzyme has a fairly high Km. So that means that this is not going to be active unless you have very high sugar concentrations. So, and you can see that this is around, or it's a bit higher than the sugar concentrations that you normally have in blood. So when you have sort of high sugar concentrations, when you have hyperglycemia, then this is going to start to become active, and it's going to start to process sugar. And that's suitable in the liver and the pancreas. In the liver, this means that when you start getting high blood sugar, the liver will start to capture it and can start making glycogen, things like that. And in the pancreas, this means that when you get a high blood sugar concentration, the pancreas will start to sense it through metabolism. So that's exactly the function you want. Hexokinases, which is, carries out the same reaction, but which is a different isoform of the enzyme. It's actually kind of a dimer. This is a monomer, and it has some structural sort of differences. But hexokinase has a much lower Km. It's almost an order of magnitude down. And so this means that hexokinases will be active at very low sugar concentrations. So these enzymes are good for capturing efficiently any sugar that comes into the cell. And so these are expressed in cells which are responsive to insulin. So as soon as they are sort of allowed to take up glucose by the insulin signal, then the hexokinase will capture whatever comes in. So you can see that the Km values tell you something about in which type of situation or environment the enzyme should be operating. So we can glean some information about enzyme function from this. So I think that's a useful property of Michaelis-Menten kinetics. And you can find these values in databases like this.